Welcome students. Now we are going to see the relationship between limit point of a set and the limit of a sequence. Limit point of a set, it means that here if the set is the range of the sequence here. Range of the sequence, it means that the set is the set whose whose elements are the terms of the sequence here. So first we are going to see this theorem here. Now statement of the theorem is this. Theorem: let ordered pair X, D be a metric space and A be subset of X, then X belongs to X. Now this element is a limit point of A if and only if there exists a sequence xn of points in A, none of which equals X. It means that here now all the terms of set A are different from X here, such that limit n tends to infinity of xn is equal to X. That is, sequence xn converges to X here. Now to prove this theorem, now we are going to consider here two parts. Okay, in one part we are going to consider here when X is limit point of this set A, then we are going to show that there exists a sequence xn of points of A such that xn converges to X here. And in second part, when we have a sequence of points in A which converges to X, then we are going to show that X is limit point of this set here. Okay, so to prove this, now here first we are going to consider that X is limit point of set A. Then here we are going to show that there exists a sequence xn of points in A which converges to X here. So let X belongs to X be a limit point of A, that is a limit point of this set A. Now constructing sequence here, constructing a sequence xn by recursion as follows. Now we know that here X is limit point of this set A. So it means that here we have for every r greater than 0, now this set is always non-empty. This set, it means that here if you consider now this open sphere here, now this open sphere whose center is deleted and its intersection with now set A is always non-empty for every r greater than 0. So we are going to use now again and again here. So we write here, taking x1 belongs to now this set open sphere S1x whose center is now deleted here. That is, this is the open sphere of radius 1 intersection with now A. Now remember, this is possible. This is possible since x being a limit point of set A here, of A. Okay, so therefore we have here now intersection of this open sphere whose center is deleted with A is non-empty. Okay, likewise the points, now we can select now x2, x3, x4, x5 and so on. Okay, likewise the points now x1, x2 and so on xn have been chosen such that xi belongs to now this set. Okay, yes, 1 upon I. Yes, xi belongs to now this open sphere. Yes, 1 upon I. Now this is the radius of this open sphere. Okay, whose center is deleted. Intersection with now A for I is equal to 1, 2, 3 and so on up to n. But now here x is limit point of set A. So still now this set, that is yes 1 upon n plus 1 x minus singleton x intersection with A. Now this set is non-empty here, so I am using this. Now this is not equal to 5. Okay, now still now this set is non-empty because now x is limit point of this set. So it means that here it is possible to choose x suffix n plus 1 to be a point of this set, and this procedure is repeated now infinitely many times. Thus the sequence, so using this we can create the sequence xn here. Thus the sequence now xn has been constructed by recursion. All the points. Now here we are writing this sequence xn here now, but this sequence is the sequence of points of A also. Okay, because we are taking now this open sphere and this set here. Okay, now here points of this sequence are now common to these two sets here. So all the points of which are in A and none of which equals x here. Now let epsilon greater than 0 be given and let capital N be a positive integer, such that now n is greater than 1 upon epsilon. Okay, then we write here, now xn belongs to now this open sphere, yes, 1 upon n x. Okay, that is the open sphere whose radius is 1 upon n, and this open sphere is containing now yes epsilon x. Okay, for all n greater than n. Okay, now here remember, now n is greater than n here, and this n is greater than now 1 upon epsilon. So this implies that we write here 1 upon n now is less than 1 upon capital N is less than epsilon. So this implies that if you consider this open sphere, okay, yes, 1 upon n, okay, that is the open sphere whose radius is 1 upon n. Okay, then this is obviously containing now this open sphere whose radius is now epsilon here. Okay, so we write here, now xn belongs to this open sphere, yes, epsilon x, for all n greater than n. So now meaning of this is that, yes, meaning of this is that actually here distance between xn and x is less than epsilon for all n greater than n. That is, the sequence xn has limit x here, or the sequence xn converges to x here. Now limit n tends to infinity of xn is equal to x. Now in the converse part, now we are going to consider now the sequence xn of points in A, none of which equals x, and the sequence xn has limit x here. Then we are going to show that now x, the limit of the sequence, that is x, is the limit point of the set A here. So we write here conversely, assume that there is a sequence xn of points of A here, none of which equals x. That is, now all the terms of this sequence are different from x here, such that limit n tends to infinity of xn is equal to x here. Now here, now limit of this sequence is x here. So therefore, that is, this sequence is convergent. Therefore, for a given epsilon greater than 0, there exists a positive integer. Capital N, positive integer capital N, such that now distance between xn and x is less than epsilon for all n greater than n. That is, we write here now xn belongs to now this open sphere, okay, yes, epsilon x, that is the radius of this open sphere is epsilon and center is x for all n greater than n. Now this sequence is the sequence of points of A here. Now xn is member of now this open sphere. So meaning of this is that, okay, here we have yes epsilon x minus singleton x, that is the open sphere whose center is deleted. And if you take now intersection of this set with A, then this is non-empty. Okay, this is non-empty. So we can say that here, hence x is a limit point of the set A here, of the set A here. Now next is corollary. Now in corollary we are going to see what is the relationship between now closed set and the convergent sequence in that set. So corollary is that, corollary, now statement is this: let ordered pair x comma d be a metric space and now A be subset of x here. Okay, then the set A is closed if and only if every convergent sequence of points of A has its limit in A. It means that if you take any closed set, then any convergent sequence in that set has limit again in set A. Okay, again that is in the same set here. Okay, or when you have this, if you take a sequence here, okay, or if you take a convergent sequence in a set, okay, and if that sequence has limit again in that set, that is, this is true for every convergent sequence of that set, then we say that that set is closed here. So for example, now if you take x is equal to RU, that is R with usual metric, and here if we take this now, okay, now we know that now closed intervals are closed sets in this set. Okay, now here if we take now this sequence, xn is equal to now 1 upon n. Now this is convergent sequence in this set, okay, and this sequence has limit 0, okay, or this sequence converges to 0, and this is again in this set A. So using this we can say that now this set is closed, because if you take any convergent sequence of points of A, okay, then that sequence always converges to an element which is again member of this set. Okay, now if you consider again now this sequence, now n minus 1 upon n, okay, this is the sequence of elements of this set here. Okay, now here if you take now n greater than or equal to now 2 here, okay, then in that case, okay, now this sequence converges to now xn. Now this sequence has limit now 1 here, and which is again in the set A here, okay, which is again in the set now A here, now 2 minus 1 upon 2. So first element now here 1 minus 1 upon 1. It means that now all elements are here from the set A, because we know that now here n minus 1 is less than n, so n minus 1 is less than here n minus 1 upon n is less than this one, and this is now for n is equal to 1 we have 1 minus 1 upon this, so we write here this is greater than or equal to 0 here. Okay, now next is this theorem. Now in this theorem we are going to see the relation between now limit point and the limit of the sequence. So statement of the theorem is, let xn be a sequence in a metric space, x comma d, such that limit n tends to infinity of xn is equal to, we have x, then okay, just a minute, here let A be the range of the sequence, A be the range of the sequence xn, that is, here now this set A is the range of the sequence xn, then now first statement is that if A is a finite set, then we have xn is equal to x, for infinitely many n, then we have xn is equal to x for infinitely many n, that is here okay, in that sequence we have xn is equal to x for infinitely many values of n, that is in that sequence we have same terms for infinitely many value of n here. Okay, then second is that now if A is an infinite set, then x is the limit point, of the set A. So this tells us that if the range of the sequence is an infinite set, then in that case the limit of the sequence, now limit of this sequence is x here, now the same element x is the limit point of that set A here, okay, which is the range of the sequence xn here. किती झालं आपलं? नाही किती झालं? अजून एक थेरम आहे, मग अजून 10-15 मिनिटं होईल गाड्या. नको, राहू दे हे पुसण्यामध्येच. Now we are going to see one theorem on convergent sequences in the product matrix space. Now statement of the theorem is this. Theorem, let x comma d1 and y comma d2 be two matrix spaces. A sequence. Now this sequence xn comma yn in the product matrix space. X cross y converge to element x comma y if and only if the sequence xn converges to x in capital X and sequence yn converges to y in y. Now to prove this, now we are going to consider a product metric here D. So now proof of this theorem. Now consider the product metric D here. Consider the product metric D, which is defined as here D of x1 comma y1 then x2 comma y2. Now this matrix is defined on x cross y here, okay, which is equal to now d1 of x1 comma x2 plus d2 of y1 comma y2, where here we have x1 comma y1 then x2 comma y2. Now these ordered pairs belongs to now this set x cross y, okay, that is now this ordered pair x1 comma y1 and x2 comma y2 now belongs to now this set here, okay. Now remember that here now since d1 and d2 are two matrix spaces here, now d1 plus d2, okay, d1 plus d2, it means that d1 of x1 comma x2 plus d2 of y1 comma y2, okay. Now this addition, okay, this addition is again a metric space, so therefore D is a metric function on x cross y here. Now assume that here xn converges to x in x and yn converges to y in y, okay. Then by using definition of convergent sequence, then for each epsilon greater than 0 there exist positive integers here n1 and n2 such that now d1 of xn comma x, now since this sequence xn converges to x in x, so we write here d1 of xn comma x, this is less than epsilon by 2 for all n greater than or equal to n1, and now yn converges to y here, now this sequence converges to y in y, so therefore we write here d2 of yn comma y, now this is less than epsilon by 2 for all n greater than or equal to n2. Now we are taking here epsilon by 2 and again here epsilon by 2 because we are going to use this and we are going to prove that now that is now this sequence, okay, xn comma yn converges to x comma y, that is here in that case we are going to show that now d of xn comma yn comma x comma y, now that is less than epsilon, okay. So that's why we are taking epsilon by 2 and again epsilon by 2 here. Now taking n is equal to now maximum of n1 and n2, that is consider maximum value from these two numbers n1 and n2 and then take that value as n here. So therefore we write here d1 of xn comma x, this is less than epsilon by 2 for all n greater than or equal to n here, and d2 of yn comma y, Now this is less than epsilon by 2 for all n greater than or equal to n, where n is maximum of n1 and n2. Now d of xn comma yn comma x comma y. Now this is the sequence here and this is a point, so which is equal to, we write here d1 of xn comma x plus d2 of yn comma y. So this is the definition of d here, but we know that now this is less than epsilon by 2 and this term has value less than epsilon by 2 for all n greater than n. So that's why we have taken epsilon by 2 and epsilon by 2. So therefore we write here d of xn comma yn comma x comma y, that is this ordered pair, this is less than now epsilon by 2 plus epsilon by 2 for all n greater than or equal to n. So therefore we write here d of xn comma yn comma x comma y, that is this ordered pair, this is less than epsilon for all n greater than or equal to n. So this tells us that now this sequence xn comma yn, now this sequence has limit x comma y, or this sequence xn comma yn converges to point x comma y here, converges to a point x comma y here. Now for the converse part, now we are going to consider convergent sequence, that is this sequence, that is xn comma yn converges to x comma y. Then we are going to show that xn converges to x in x and yn converges to y in y. Okay, so conversely let xn comma yn, now this sequence of x cross y converges to x comma y in x cross y. Then for each epsilon greater than 0 there exists a positive integer, now capital N, such that d of xn comma yn, this ordered pair, comma x comma y, that is this ordered pair, this is less than epsilon for all n greater than or equal to n. So we write this by using definition of convergent sequence. Okay, so this implies that now using definition of d, we write here d1 of xn comma x plus now d2 of yn comma y. Now this is less than epsilon for all n greater than or equal to n. Now sum of these two is less than epsilon, so this implies that now d1 of xn comma x, this is less than epsilon, and d2 of now yn comma y, now this is less than epsilon for all n greater than or equal to n. Now meaning of this is that here xn converges to x and yn converges to y here, that is we get here now xn converges to x in x and yn converges to y in y. So this is for this lecture. Thank you.